I know I said things about this in the videos I posted for the Calculus 1 review, but I know that not all of you have watched those. That's fine. So here it is, just a brief spiel. Imaginary exponentials. So imaginary exponentials are like super useful. In a nutshell, here they are. E to the I theta is cosine theta plus I sine theta. That makes e to the minus I theta cosine theta minus I sine theta. Now, basically, guys, the imaginary exponentials, and the formula I just wrote there are known as Euler's formulas. For us, you can just take them as a given fact. I wouldn't try to derive them just yet. We can derive them later in the course in a certain way. They're just wonderful vehicle to remember trig identities. So if I add these two equations, I get e to the I theta plus e to the minus I theta is equal to 2 times cosine theta. If I subtract these equations up here, I get e to the I theta minus e to the minus I theta is equal to 2i times the sine of theta. So you see what these calculations show us is that I can write cosine and sine both in terms of the exponential of imaginary quantities. And the good news is that despite the fact that you don't know a lot about complex analysis yet, it's relatively safe to use these. They obey ordinary laws of algebra. Let me show you how. But before I do, just pause for a second here. Any questions about what I've written so far?
Should it be 2i cosine theta?
No. So this is from adding these equations. This is from subtracting. It's okay. But these give us a way to understand sine and cosine in terms of imaginary exponentials. So with these in hand, we can do things like calculate the cosine of theta times the cosine of beta. What's the cosine of theta times the cosine of beta? Why would you care about that? Well, I might ask you to integrate that. Right? What if I asked you to integrate the cosine of 2x times the cosine of 5x dx? What would that be equal to? It's not covered by the techniques we've done so far. You need to know trigonometry that you might not know. Here's how you can derive that trigonometry. So I just take cosine theta and cosine beta, and I replace it by this, imaginary exponentials. Like so. And then you just multiply like normal. It's like, you guys tell me, if I take, so 1/2 times 1/2 is 1/4, all right? So I have e to the I theta times e to the I beta, just distribute, all right? Plus e to the minus I theta, e to the minus I beta, plus e to the I theta, e to the minus I beta, plus e to the minus I theta, e to the I beta. I just multiply them out, all right?
Can you put those together? Where they go like I squared theta beta?
Well, how do you think these add? What happens with these terms? This would be e to the I theta plus I beta. You could factor out the I, and you got I theta plus beta. This would be e to the minus I theta minus I beta. So factoring out the minus I. This guy, we have e to the I theta minus beta. That guy, e to the minus I times theta plus beta. Theta minus beta, rather. I'm a little bit sneaky in the last step there. What did I do? Let me be a little bit more explicit here. It's like e to the minus I theta plus I beta is e to the minus I times theta minus beta, okay? That's what I did there to get from this guy to that guy. I think the other ones are pretty clear. So then, what you do is just a matter of identification, right? This is a cosine. If I bring in a half, so I've got 1/2, take a half inside, take another half over here. That's straight up cosine theta plus beta. That is 1/2 cosine theta minus beta. Yay, trigonometry. So we have now a new identity. Cosine theta, cosine beta is 1/2 cosine of the sum of the angles plus 1/2 the difference of the angles. Which is amazing because with this identity, well, actually, by the way, if you know this, you can do what? If you differentiate it with respect to theta, you get a what? You get a sine cosine identity. If you differentiate it with respect to theta and with respect, and then after that differentiate with respect to beta, you get a sine sine identity. In the quiz, I ask you to try to derive the sine sine identity using a calculation like I just did. I'm totally cool with you also just deriving it another way if you want, though. Like you could derive it by just differentiating this identity if you wanted to, but I think it's worth your time to spend a couple minutes learning how imaginary exponentials derive trig identities because it'll allow you to remember all of them. It's got a little bit of a startup cost, but it's not much. So this is actually 1/2 cosine of 7x plus the cosine of 3x. So there you go, 1/14 sine 7x plus 1/6 sine of 6x. And you can do a very similar calculation to do like sine sine or sine cosine. Here, let me show you something else while I'm at it. If we do sine theta, cosine theta, that's equal to what? 1/2i e to the I theta minus e to the minus I theta times 1/2 e to the I theta plus e to the minus I theta. So if I multiply this by 2, I just go with it. So I got 1/4i. What happens when you multiply this? You get e to the 2I theta minus e to the minus 2I theta. And then if you look at the cross terms, see this and that, and this and that. We're multiplying something like e to the a times e to the minus a. But what's that? That's 1, right? Those are multiplicative inverses. They're reciprocals of one another. So both of those products just give you the quantity 1. But there's a plus minus and a plus plus, right? So those terms just straight up cancel. It's 1 minus 1. And you're just left with what I wrote. But what is what I wrote? You got to use your imagination a little bit. So the key is to be able to massage things back into the formulas for sine and cosine that I wrote up here and make an identification. So what is this? To quote Cooney from UHF, what's in the box? Sorry, it's a too obscure a reference.
Sine.
No, nothing, absolutely nothing.
Okay.
Oh, I'm sorry, I shouldn't call students stupid. Let's see here. No, what did you tell me? It was sine, what was it? It was sine?
It would be sine 2.
Sine of 2 theta, yeah. Making the substitution 2 theta for theta up here, right? So What have we done? We have just calculated the identity for sine 2 theta. How did we find it? By doing algebra on the imaginary exponentials. You don't have to learn this, but if you do, it's very useful. You do have to know trig identities, though. So, uh-oh, I think I just erased the board a little bit on my shirt. Well, guys, any questions about the homework? We still got 10 minutes. If not, get out of here. Oh, quizzes. Oh, my goodness. Yeah, you can turn it off. Thank you. I am very